On the other hand, if we have dependent events A and B, that is, one affects the other, we have to take into account that affectation, as it were. So when we look at the probability of A and B, depending on whether A affects B or B affects A, it's a matter of notation, we either get the probability of A times the probability of B given A, that is, the probability of A happening multiplied by the probability of B, operating under the assumption that A has already occurred, or if we go the other way, the probability of B times the probability of A given B. It depends on which comes first and how we want to talk about that idea of dependence. But in any case, we have a couple of pretty straightforward examples that we can look at here to understand them. So first, we want to find the probability of selecting a queen and then selecting a king from a standard deck of 52 playing cards without replacement. So for this, if we're talking about the probability of getting a queen and getting a king, we have to understand here that we are looking at multiplication. The probability of getting a queen, which I'm just going to denote Q because I'm low in space. And then we're going to multiply that by the probability of getting a king, where because we've already drawn the queen, there are less options from which we get the king. So that would be king given that we already have a queen. So for the queens, well, there's 4 of those out of 52 total cards. Meanwhile, for king given queen, I don't know what happened there, we have 4 kings, but now only 51 cards. So if we multiply out those probabilities, we will get 16 out of 2,652 total options for a probability of about 0.006. For another example, we have that 18,187 U.S. allopathic medical school seniors applied to residency programs and submitted their choices. Of these, 17,057 were matched with programs, with about 79.2 getting into one of their top choices, where medical students rank their programs in order of preference, and directors in the U.S. rank the students, where we get a match if a student's preference and a director's preference overlap, resulting in the placement of a student in a residency position. And what we want to do is find the probability that a randomly selected senior was matched with a residency position and it was one of their top 3 choices. So here, we're doing something again like this, but we're kind of given the 2 parts separately and we're being told to put them together. So, if we're going to let A refer to the event of a match, and B refer to the event that they get a top choice, then we have that the probability of A is that value 1757 over 18,187. That is the probability of them getting a match comes from the 1757 who matched divided by the total number who applied. Meanwhile, for the second choice, we don't get the probability of B directly quite so much as we get the probability of B given A. The probability of a match, or the probability of a top choice given that they got in, where this is 79.2%. So if we want to find the probability that they match, and that the program they match with, is a top choice, the probability of A and B, using this idea for dependent events, it would be the probability of A times the probability of B given A, which here